Thank you very much, Eva, and thank you very much for the organizer. It's a great opportunity for me to introduce the PHASE and topology properties, and also Wannier tools to the community. Yeah. I'm from EPFL. I'm QuanSheng Wu, and yeah, let's start. Okay. Yeah, here's the outline. Our talk will divide into two parts. The first one, I would like to introduce the theory parts about the Berry phase, Berry curvature, and also try to introduce the Wannier charge center. Sometimes it's also called the Wilson loop. And also I will introduce the bulk edge correspondence, which is very important for the topological systems. And then I will introduce the applications on the HALDANE model, wire SEMIMETAL and quantum spin hole, and the topology insulators. Let's start with the type of orders. I mean, until 1980s, all the ordered phase could be understood the symmetry breaking as what we learned from the textbook. For example, take an example of the gas. Let's think we have a carbon gas. And in the gas system, we have all three rotation symmetry, and also we have continuous translation symmetry. Then let's try to cool down the system. If we cool down the system, then the gas will try to, the carbon will try to cool down, and then the O3 symmetry or the continuous symmetry will break until it forms our crystal structure. For example, here for the carbon, we have two kinds of, here we list the two kinds of phase. The first one is the diamond, and the second one is the graphite. These two systems have different crystal symmetry. Yeah. This is how we understand the symmetry. I mean, how we understand the order of the phase. There's other examples. For example, the magnets. This magnets breaks the time reversal symmetry and the rotational symmetry of the spins. And also, for example, for the superfluid or superconductivity, it breaks the internal U1 gauge field symmetry. In 1980s, there's another kind of ordered phase come out, and it's not related to the symmetry breaking. This is called the quantum Hall effect. Let's start with the Hall effect. Okay, this is a 2D electron gas. We apply the magnetic field along the Z direction, then apply the current along the X direction. Then we due to the Lorentz force, we can get the Hall voltage along the Y direction. Then we can get the resistivity Rxy. And in the low magnetic field, it's a linearly increase, the magnetic field increase. Okay, but if you look at this plot, you will find that as we continuously increase the magnetic field, you will see here we have a plateau, and another plateau. And if we calculate, and if we get the whole resistivity, and we will find that the conductivity is just an integer times E squared over H. E is the charge, the electron charge. H is the Planck constant. And this N is an integer. And what does this integer means actually? This integer is a real integer. And what does it mean? If you measure the conductance here, this plateau is exactly precise flat. The precision could go up to 10 to minus 9. It's really, really high. But one strange thing is that when we do the measurement, the material is not perfect. There are lots of disorders, and there are lots of vacuums or dopings, and also it's measured at the room temperature. This is super weird, actually. So why it's so precise? Okay. To answer this question, actually this is a topology protected. So we need to introduce the topology concept. Actually, the topology comes from the mathematics. it defined like this. If you have two objects, if they are topologically the same, then it means that they can be deformed continuously into each other without cutting or pasting. For example, let's start from a ball, and if you squeeze it a little bit, it's become a egg shape, and then you make like this as a pot-like. It's also pot-like. Those 5 objects, they are topologically the same because you didn't cut, you didn't paste anything. But suddenly you make a hole here, you make a pole, then it means you cut the system. Then in this case, this system is topologically different from the previous one. And then you continue to shrink, you continue to deform it until you have another pole. And if you look at it, then the topological number is what is the number of holes in these 2D closed surfaces. Okay. So it means that, I mean, by the deformation, the shape of the object change a lot. So it means that this topological invariant doesn't depend on the local details, right? But how can we calculate that? In order to calculate that, actually, we can calculate the topological invariant using the local quantity. This is called the geometric quantity. For example, for the two-dimensional surface, we can introduce the Gaussian curvature. The Gaussian curvature is defined as the inverse of 2 radial curvatures. For example, like this. For example, for this shape, the curvature is negative, and for the cylinder, it's 0. For the sphere, it's positive. There is a theorem in the mathematics. It's called the Gaussian bonnet theorem. It says like that: the area integral of the curvature over a closed surface M is quantized, and it's a topological invariant. So if you integrate this one, so let's look at the sphere. For the sphere, the curvature is 1 over r squared, and then we know that the area of the surface is 4 pi r squared. So the integral around the surface is just 4 pi. So we know that this chi is 2. And for the torus, here we have half of the negative curvature, and we also have half of the positive curvature. So in total, they cancel out. So the integral is just 0, so chi is 0. And we can reform it as another integer. This is called the genus. And for the sphere, genus is 0. For the torus, the genus is 1. Actually, if you look at the another torus, for example, make another hole on the surface, then the genus 2. So this genus is exactly the same as the number of holes of the 2-dimension closed surface. So here, it provides a method to calculate the topological invariance by using some local geometric quantity. Actually, most of the topological invariance in physics also arise of the integrals of the some geometric quantities. Let's go back to our crystal system. In the crystal system, the potential is periodic. So we have the Bloch theorem. That means that, it tells that one electron wave function in the crystal can be written as a Bloch wave function. You have 2 parts. One is a periodic part, and no, sorry, this is a plane wave part, and this is a periodic part. And in the crystal, you will have a crystal momentum. This is called K, and yeah, and we know that since it's a periodic, so this K, it's all the K points from the Brillouin zone. If we look at the first Brillouin zone, actually it's closed. It's like a torus. For in the 2-dimensional system, it's a 2D torus, and in a 3D dimension system, it's it's a 3D torus. Okay. So we have, analog to the previous case, we have a closed phase, right? Okay. And we can think like that. For example, here we have a 2-dimensional brane zone, and we have each K point. And this is a kind of bundle, the bundle, and there's a fiber bundle. It gives you the wave function. And so now we have a closed surface. The next thing is that we need to build a curvature, right? Okay. Then the curvature is built by, it's called the barrier curvature. So the next question is, how can we define the barrier curvature? Let's start from the barrier phase. The barrier phase is kind of a geometric phase, and it's introduced in the quantum mechanics by Barry. And he argued that in the adiabatic limit, the Hamiltonian is changed slowly, very, very slowly. So the system remains in its time-dependent ground state. And in this case, the wave function will evolve like this. This is the time-dependent ground state, and you will have a dynamic phase. This is how we know that in the quantum mechanics we have dynamic phase. But additionally, you will have a geometric phase, and this phase is called the barrier phase. And it doesn't depend on time, and it only depends on the geometry of the path. It means it defines like this. The phase is for example, let's consider a closed path like this one. This is a closed path, and the barrier phase for this closed path is a closed integral of this quantity. This quantity is called the barrier connection. Okay. So if you look at this part, you will see that it doesn't depend on the time. It means that no matter how fast or how slow it be, then the phase for this closed path is the same. So in the crystal systems, K is the parameter lambda, and the barrier phase is defined like this. And here the periodical part of the wave function is the hero in the barrier connection. Okay. Let's study a little bit more about the barrier phase. What kind of property it would be? We know that for the wave function, we will always have a phase factor. I mean, there's a freedom choice of the phase factor. This is called the U1 gauge freedom. Okay. So for each K point, actually we know that for each K point, the Hamiltonian is diagonalized independently, right? Anyone is raised the hand? No. Okay. No, it's not about me. Okay. So I would like to take the question after my talk. Okay. So okay, thank you. Okay, let's go back to the wave function. So at each K point, the Hamiltonian is diagonalized independently. So it means that the wave function will have a K-dependent phase. And this phase is K-dependent because we don't know in which K, I mean, for different K, the phase could be different. Okay. Under this change, the barrier connection changes by a gradient. It's like this. This is exactly the same as what happens in the electrodynamics. This barrier connection, just like the vector potential, is almost exactly the same. So we can do the same analogy. Just like how we obtain the magnetic field strength from the vector potential, we can get the barrier curvature by taking the curl of the barrier connection, just the curl of this one. Let's do a comparison between the electrodynamics and the barrier connection by phase. Okay. So the barrier connection can be compared with the vector potential. the Berry curvature can be compared with the magnetic field. The Berry phase is the integral along or closed path of the Berry connection, and it's the same as the Aharonov-Bohm phase. And the last is the integral of the Berry curvature over a closed path, over a closed surface. It's all integer. This is called the Chen number, and it's also analogous to the Dirac monopole. But actually, in the real system, the integer is 0. But if we have the magnetic monopole, then we could have the integer. So this is the analogy. So now, for now, we have the curvature, and we have a closed phase, so we can define a topological number. Okay, so and if you study the Berry curvature, this Berry curvature is gauge invariant. So I mean, when we talk about the gauge invariance property, then we might think it may be connected with some physical quantities, right? Okay, in 1982, TKN pointed out that the integer quantum Hall effects in the two-dimensional crystal follows the integral of the Berry curvature. This is the explicit formula for the Berry curvature. So in total, in their formula, they argue that they prove that the Hall conductivity is the Chen number times E squared over H. And this is also called TKN number. Okay. So let's go to the quantum Hall. Let's back to the quantum Hall effects again. Then first, here we assume there's here we look at a honeycomb lattice. This is the graph for the graphene, and the spectrum is we have a Dirac cone here, and then we can add the magnetic field. After we add the magnetic field, we will have the lambda level, right? And let's not study the continuous limit. Let's study the discretized limit. I mean, it means that the magnetic field is so huge, so that the flux per unit cell is it's close to 1/4 of the quantum flux. So it means that the unit cell will become a supercell. So this is called a magnetic supercell. And then if you look at the band structure, these are 2D plots of the band structure. So you will find that this band structure will split into 4 parts. This is the one band, this is another band. For the top band is split into 4 parts, 1, 2, 3, 4. We have 4 lambda levels. I mean, you can think if we increase the, if we decrease the magnetic field, then we will have a larger magnetic supercell, and then the lambda levels will become, you will have more lambda levels. Okay, so we can use the Berry curvature formula, and we can calculate the Chen number for each band. You will find that for different band, I mean for the lambda bands, it's associated with some Chen number. Okay. Okay, okay, the introduction is quite long, okay. Here, I want to introduce just another way to calculate the Chen number. This is called the Wannier charge center. Let's start with the Wannier functions. Wannier function is the Fourier transform of the Bloch wave function, just the Fourier transform of it. And we can study the Wannier center. Let's calculate the Wannier center in the home unit cell. And the Wannier center is defined by this one. They calculate the position of the Wannier functions. And they will by some mathematical calculations, and you will find that the Wannier center is just the integral of the barrier connection in the Brillouin zone. So in one-dimension case, this integration is just one. So you will find that the Wannier center is just the barrier phase over 2 pi times the lattice constant A. In other words, it means that a barrier phase evolving from 0 to 2 pi would just correspond to a Wannier center evolving from X to A. Yeah. So this is very important for the next slides. Okay, let's study the two-dimension systems. Okay, for the two-dimension system, we have Kx and Ky. We have two good quantum number Kx and Ky. And in this case, we can define a hybrid Wannier function. It's defined like this. The Fourier transform is not. It's only X. I mean, you only do the Fourier transform along the Y direction. In the X direction, you keep the good quantum number for the X, for the Kx. So we can also calculate the center of the hybrid Wannier functions. It's you will do like this. It's the same as the integral of the barrier connection, but you just do the free. You just do the integral along the Ky direction. Okay. Okay. So for example, here you have so the integral is doing like this. So select the one Kx and do the integral from this to that. This is a closed path. So for each slide, you will get a barrier phase, right? So for this one, you have, for example, in this case, you have a barrier phase here. And for this slide, you have this one. For this slide, you have this one, and this one. Here we have another case that you have different values. It evolves like this. So this evolution we call the Wannier charge center evolution. Okay. So what the use of this one? We can prove that. I mean, we can prove that the Chen number is only related to the value from the starting point and the end point. It means that, for example, here the Chen number is 0 because the starting point is 0, the end point is 0. And for this case, the starting barrier phase is 0, but the end of barrier phase is oh, sorry, the end of Wannier charge center is A1. Sorry. Okay, what the Wannier charge center actually is the same as the barrier phase. It's just a unit change by A1. Okay, so it means that we can just get the Wannier charge center by just calculate the hybrid Wannier function center. I mean, evolves along some K direction. Okay, so this is another way to calculate the Chen number. Okay. And with this, we can with this hybrid Wannier charge center, we can try to understand the quantum Hall effects, why it's quantized. Okay, let's take a two-dimensional geometry. It's like this, and it's periodic along the X direction, but it's confined along the Y direction. The current is along the X direction, and we measure the voltage along the Y direction. Okay. So the momentum evolves under the electric field. If we have an electric field, then the momentum changes like this. And so we know that the Kx could evolve under the time, I mean, if we have an electric field. So look at this Wannier charge center plot. If we evolve the Kx, the momentum from 0 to 2 pi, then the Wannier charge the center of the Wannier function changes from 0 to A1. And then let's let's use this formula to calculate how long will it take to get this change of the K, okay? Kx, T minus kx0 is 2 pi over ax. And this is equal to this one. So we can get the time is minus 2 pi h over e ax like this one. So it means that during this time, during this time, not this time, during this period, there are C number of electrons moving along the y direction. Here in this plot, the Chen number is 1. But if you have 2 more, then if Chen number equals 2 or 3, then so the current it's equal to the E times the Chen number divided by the T0. So it's written like this. So the E square AX is C over H. Okay. So we can get the current density. Current density is IY divided by AX. So you will see that this is equals minus the Chen number E square over H times the E. And we can use the definition of the conductivity. So we can get the conductivity is exactly the same as the charge. I mean the Chen number times the E square over H. This is the proof of the quantum Hall effects. Okay. So it means that we can calculate the Barry curve. We can calculate the Chen number by using the Barry curvature, but it's not the institute. But it's not the institute to understand why the conductivity can be related to the Chen number. But if we use the Wannier charge center, then it will be much more convenient. Okay, let's go to the multi-band systems. The multi-band system, the Chen number defined for the multi system is just the sum of all the occupied bands. And we can define a projector for the all occupied states. It's like this, the integral all along the y direction, the projector. Okay. And we know that it's clear that the Wannier charge center is just the eigenvalue of this operator, the projection and the times y operator times b. This is very clear. And if we plot all the Wannier, all the bands, all the centers for all the bands together, this is called Wannier charge centers. Okay, it's like this. For example, at each k points, we have 1, 2, 3, 4, 5, 6. We have a lot of bands. For example, here we have 16 bands. Okay, so we have 16 of the Wannier charge centers. Okay. Okay. So the Wannier charge center is not only can be used to get the quantum topological number, but also it's related to the surface or edge states spectrum. Okay, let's talk about the bulk edge correspondence. The bulk edge, so let's here we have a semi-infinite system. When y is larger than 0, then this is a bulk. It's topological non-trivial. Okay, and then it's contact with the vacuum. For the vacuum, it's in the negative axis, and in the x direction is periodic. Okay, so before going on, we want to introduce another technique for the topology system to study topological properties. Okay, this is called flatten. So here, this is just a normal band structure. We have occupied bands. These are unoccupied bands. If we want to study the topological property for this gap, we can try to do a flattening, because we know that if we don't close the energy gap, the topological number will not change, right? So by the strongest limit is that we make all the energies of the unoccupied bands the energy is +1. All the occupied bands, the energy is -1. So here they have, this is the Hamiltonian. Hamiltonian can be written like this. And by a flattened Hamiltonian, you can write just like this, 1 - 2 of the projectors onto the occupied state. And the topology of these two Hamiltonian is exactly the same, because by the flattening, we don't close the gap. Okay. So let's back to the semi-infinite system. The semi-infinite system, the flattened Hamiltonian should like this. So for y is larger than 0, it should exactly the same as the bulk Hamiltonian. So it's a 1 - 2b. So for y smaller than 0, it's just a vacuum. So it's just 1. So in a compact form, it's like this. You can write it's p times v0 y p or 1 - p. Okay. Then this Vy is this form. So you will see that for example, for y is less than 0. Okay, y is less than 0. Then this is 1, 1. It's p square. P square equals to p. So it's p times plus 1 - p is just 1. Okay, this is the same as this one. So this is our compact formula. Okay. Then let's try to study the spectrum of this semi-infinite system. We will see that this Hamiltonian includes the spectrum for the for the flat for this one, and also for the one. So the other states that's not included in so the bounded states, the boundary states, or the in-gap states could just include in this term, this p, v, y, and p in this term. And it's like this. And let's remind you that the Wannier charge center is the eigenvalue of this quantity. And this v is just a y. Okay. Then if we can build a continuous evolution between this operator to this operator, then we will know that the spectrum are the same, right? Let's can do this. Okay. In this case, the v0y is this form. Okay. It's a step function. Then we evolved a little bit. Actually, it's not exactly a step function because the potential close to the surface is exponentially decay. Actually, it's more like this. Okay, and then we can evolve a little bit like this. We can just turn it like this. Okay, and then in the end we can evolve to this one. It can be proved that in this paper is proved that the evolution of the evolution of this one will not close the gap. So it means that we can prove that the topology of the Wannier charge center spectrum and the physical boundary is exactly can be identical. So it means that for example, let's take an example. So this is the Wannier charge center for the HALDANE model. If you look at this one, it's just trivial because the Chen number can be calculated by getting minus this one to this one. It's just 0. But so if you look at the edge states, it's just a trivial. Why it's trivial? Because it doesn't connect from the bulk to, it doesn't connect the conduction band to the valence band, and you can continue to deform this edge states into the bulk, so that there will be no edge state anymore. Okay, but in this case, the Chen number is 1. Why is here we have a jump? Because we we do a modulo of the lattice lattice constant. If you connect, if the Wannier Chern center touch the boundary, then we will put it to 0. So the Chern number is just it accumulates the center from this one. Here we accumulated this part, and in this case we accumulate this one. So in total, the Wannier Chern charge center evolves is 1. So the Chern number is 1. So if you look at the edge state, so you will see it's also connected from the bottom to the top. So it means that the topology of this one and the edge state, the Wells loop and the edge state, they are exactly the same. This is a very useful. Sometimes, for example, even the Chern number is 0, but the Wells loop is strange. It's not the Wannier. I mean, the Wannier Chern center is not. It's strange, or it's continually connected from the bottom to the top, and you will see this kind of surface state connection on the edge state on the surface. Let's go to the some applications. The first one is the HALDANE model. This is a toroid model to realize the quantum anomalous Hall effects. The quantum Hall effects, we need the magnetic field, and HALDANE introduced another mechanism that doesn't depend on the magnetic field. He introduced next nearest hopping T2, and this hopping is not real, but it's complex. It complex means that it breaks the time reversal symmetry, and he also introduces introduced the onset energy, a lot of onset energy M to break the stability symmetry. Okay, and we know that if the hopping if the next near the hopping is and the onset energy is 0, then it becomes just a model of graphene. Okay, here's the phase diagram. We will by tuning some parameter, you will find that there are 3 phases. One is the Chern insulator. Here we have you will have a non-trivial Chern number, and the outside is just a trivial insulator, and the boundary is a gapless phase. Okay, so let's choose a parameter. First, let's make T1, T2, the next near the hopping, and the onset is 0. Then this is a graphene model. You will have the Dirac constant at the K and the K prime points. Okay. And if we only add the stability onset energy, but we don't have the next nearest hopping 0, then it means M divided by T2 is infinity. It's outside of these 2 regions. It's either here or in the bottom. So this is a trivial insulator. Here you will see this is the insulator. If you calculate the Chern number, then you will find it's just a trivial. And if you plot the edge state, it's also trivial. They are identical. And if you choose the parameter inside this region, for example, choose a point here, then if you look at the band structure, this is almost the same as the previous one. And from the band structure, you can tell nothing because it's gapped. There's no any additional information. But if you plot the Wannier Chern center, you'll find that it's non-trivial. You have a Chern number equals 1. So the edge state is non-trivial. Okay. In the tutorial session, we can dig more about the HALDANE model. For example, we can study the Barry curvature and how how this system evolves from trivial insulator to a Chern insulator. Okay, let's the next example is the WEYL SEMIMETAL. we know that the Chen number is defined as the integral of the Barry curvature enclosed in the momentum space. So in the 2D system, it's just a Brillouin zone is closed. So this Chen number is a 2-dimensional property. Okay. So in 3D case, we have a 3D Brillouin zone, right? It's a 3D sense. But in the 3D system, we still can define this Chen number. For example, you can select a closed slides here. Yeah, okay, this is a Brillouin zone, so this is closed. So we can also calculate the Chen number for this case. For example, if the Chen number for the kz equals 0 is 1, and for the kz equals pi is 0, so what will happen? Okay, so what can be? So is it possible that this system is just a gapless? Actually, this is not possible because we know that the Chen number is protected by the gap. So it means that if the system remains always gapped, then the Chen number will not change. So it changed. So the thing is that there must be some gaplessness between this plane to this plane. So this is how Y points come out. Okay, let's study a two-bandoid model in this case. And here, this is the band structure. You will find that along the gamma to the Z direction, you will have a crossing point here. Actually, if you look at all the band touch point, you will only find two points here. This is the gapless states. So we have this one. So if we look at the Wilson loop at the kz equals 0 plane, at this plane, then you will have a non-trivial Chen number. This is the 1. And if you look at this one, the Chen number is 0. Okay. There's another way to choose a closed surface. Let's try to deform this surface a little bit. We try to move this down up, and this is up, and this up, and then in the end, you can form a sphere to enclose this Y point, right? And then if by the deformation, the integral of the Barry curvature will not change. So it means that there must be some source of the Barry curvature from this node point, from this Y point. So that is so it means that if we have a Y point, then it becomes a source or the drain of the Barry curvature. Okay, let's also can talk about the surface states of the Wilson methods. Okay, here is a review, and we know that if we have if we have a closed surface like this X and Y direction, if the Chen number is non-zero, if we cut the edge, then you will have a non-trivial edge states, right? Okay. Then we can then let's start the 0, 1, 0 surface element. This is the cuts along in the front. So we know that so in the middle, kz equals 0, we have non-zero Chen number. So we have edge state, and if we plot here, this is a cut. Actually, this is a cut from here. You have edge state, but for the kz equals pi, the Chen number is 0. So it's just a gapped state. It's just a gapped box state. There's no in-gap states. So it means here there's no edge state. So it's become very interesting that the Fermi surface is just become an arc. It's not a closed surface. So this is the strange Fermi arc states in the Wilson method. Okay. Okay, it's maybe okay. I will introduce another quickly introduce another analysis system. This is called the quantum spin hole system. So previously, we just talk about the system that breaks the time reverse symmetry. We have the chain number. So, but if we have time reverse symmetry, then the barrier curvature is just an odd, it's an odd function. So the chain number is just 0. So that means that for all the time reverse symmetry preserved system is just trivial? No, the answer is no. I mean, let's consider these two cases. If you have two spaces that they are related by the time reverse symmetry, and these two spaces have opposite non-trivial chain number C plus or C, C plus or C minus. Actually, for each space is non-trivial, right? But in total, the chain number is 0. But we still can define another integer number. This is C plus minus C minus. This is an integer, right? So this could be non-trivial. Okay. So in 2005, Ken and Mali, they extended the HALDANE model. They just double copied the HALDANE model. In the HALDANE model, it's spinless. So they take a spin up HALDANE model like this, and spin down is the time reversal image of the spin up. So it means that the phase is just here. The phase is the flux is a phi. Here is a minus phi. So okay, if you study the Wilson loop for spin up part, then the chain number is 1. For the spin down part, it's minus 1. So and their time reversal related with each other. So if you put them together, it's like this. Okay, so this is kx equals 0. This is called the Kramers pair point. So at the Kramers pair point, due to the time reverse symmetry, so it's always double degenerate. So in this case, it's also double degenerate points. So in this case, we can define a topological number. This is called the Z2 number. And in this case, we only need to study half of the of this path, because this part is just the image of this part. So the Z2 number is defined if you cut us. So if you cut a line here from the left to the right to the middle, and then to check how many times it crosses the Wilson loop. If it is the odd number, then it's trivial. If it's if it is odd number, then it's non-trivial. If it is the even number, then it is trivial. Then this is the Z2 phase. Okay. So in our example, we prepared one example. This is called the 1T prime tungsten telluride. And in this case, we want to mention that the imaginary next near hopping can be realized by the spin orbit coupling, and this is also described by the by kind of band inversion of the band structure. For example, here the bands are just inverted like this. Okay, this is proposed by the Bonnewick, Hughes, and Shouchen Zhang. Okay. Okay, this is the Wilson loop of the 1T prime tungsten telluride. Okay, if you look at the Wilson loop, it's connected. The connection of the Wilson loop is the same of the connection of the edge states. Okay, and okay, due to the time limits, I just will skip the 3D topology insulators. In the 3D topology insulator, it's a little bit more complicated because the topological number will be, you will have a 4 indices. Okay, and okay, and we will study this system in the tutorial. Okay, let's skip it. Then in conclusion, we introduce some preliminaries of the barrier phase and topological properties. And there are lots of details that are not mentioned actually, but you can read the reference in the marked in the slides. Okay, and we also briefly introduce this HALDANE model, Western metal, cornerstone hole, and 3D topology insulators. Actually, there are a lot of physical properties that relate to the bulk topology, especially related to the barrier curvature. That is not talked into in my slides. This includes the anomalous hole conductivity, orbital magnetization, spin hole conductivity, the barrier curvature dipole, and the kinetic magnetoelectric fields, and even the shift current. So all those properties can be calculated using latest Wannier functions, the Wannier lattice. Okay, thank you for your attention.